bad incentives in machine learning, and really the content would be about the same. So again, so what do I mean by that? Like, what are these bad incentives? So I guess like before, I sort of get started, like just a brief intro on who I am. Pretty much like I'm starting Monday as a partner engineer on the PyTorch team. So that's something I'm very excited about. But honestly, all the places I've ever worked at have been amazing. I was very, very lucky to work there. But yeah, so the purpose of this talk is really talking about this article I wrote. So this is sort of my claim to fame. It was like an article that went very popular. It struck a lot of nerves and brought out a lot of emotions in people. And so I thought like we'd explore a bit of the ideas in this post and dissect them a bit more in more detail and give you some follow-ups that I've thought about ever since writing this, because this was a while back. So, and the article, like really, I started off by making this, bold claim that machine learning researchers are basically the new medieval Catholic priests. And what I meant by that was it's basically work that's risk-free. So think of something like doing incremental work on BERT. It's high prestige because, oh, you're a professor, you're a researcher, you're a scientist. Like these are titles that come with a lot of weight. And it's also high income. Like if you can work at some place like Google Brain or FAIR or Microsoft, et cetera, you're going to make a lot of money doing taking very little risks, but also having like a nice allure of prestige. So this isn't necessarily bad, it just is. But just to give you some context, what this sort of started to remind me of was the way I would go, let's say, on something like CNBC Finance, and you have all sorts of like talking heads that come up and they'll make some predictions. And if the prediction is correct, their ratings will go up. And if their prediction is incorrect, their ratings will go up. And so the point here is that these are people that are their output isn't measured on how correct they are. It's really on how much interest they can generate around them. And I think ML has become something very, very similar, but I think economists and economists really started, I believe, this trend. So historically, if you look at academia, it's what I like to call a downside hedge, as in, most research should be ambitious, otherwise it's engineering, right? We know how to do it. But this also means that most ambitious work actually fails. So most research careers will actually be failures because it just takes one single success story at the aggregate to make everything good. But if you ask like the individual researchers whether this arrangement was good, like, well, not so much. So I have here to the right like two charts. I think this is what I think people perceive to be the importance of a paper. And like basically like impacts here to the right, it's higher impact. So you would expect that there's like a bunch of low impact papers, but then there's a lot of medium impact papers. And then there's like very little high impact papers. But the reality actually is that like most papers are actually very, very low impact. And then when you get to the high impact stuff, you sort of end up almost like with the single digit or a couple of dozens of labs or researchers seemingly doing all the interesting work, whereas everyone else is following. And so, like, why is the case? So again, like back to some other background here. I also called in the article "Machine Learning PhDs: The New Investment Banking Analysts." And the reason I said that is because I'll actually get by DM a lot of people tell me, I want to do a PhD in machine learning, and I say like, why? They go, well, I love research, but like if you peel the onion a bit, what they're actually saying is I want to work at FANG, or like I want to make money. And I call this like optimizing for optionality because it's sort of very similar in banking or investment banking. Like people go into these industries because it gives you good options later, not because you're interested in the thing. And I would argue that like basically ML PhD has sort of become like an extended interview for FANG at this point. And if you look at the interview process, actually, it's also very similar. So how do you get hired at a top lab? Well, one aspect is prestige. Like that's how you get through the door. Like you had a famous advisor. You went to a fancy school. But how do you actually get an offer? Well, it's really a bunch of trivia, right? So for example, like this was almost like somewhat of a real interaction I had where the recruiter was like, oh, I see you worked at Microsoft. Like, great, I passed the prestige mark. But then it's like, which activation functions do you know? And I remember thinking like, this question is so bizarre. And so I jokingly answered this, but they were like half serious, like, no, tell me which activation functions, And sort of like I think at this point, it's gotten to a point where, people are valuing the trivia as opposed to the core understanding, because the core understanding says, you just need something multiplied by a sigmoid. That generally works fine. But the trivia would say, no, like there's only these three that are good. So, and I somewhat feel that because of this emphasis on trivia, we've had like a death of first principles, as in it's become very, like, people will constantly try to keep up with the new archive papers, try to figure out like, oh, this and this new architecture will work in the following way. But then when you actually like look at the code for a lot of these proposals, you notice that they make extremely incremental changes, like often like single, like 1 or 2 line code changes where they'll change one of the matrix multiplications, and then they'll write 8 pages about it. And so this is why I like first principles, because it sort of helps me synthesize stuff so I don't have to constantly read and feel like I'm keeping up. But it also makes it very easy for me to figure out, given a new contribution, how impactful do I think it actually is. And I also think deep neural networks are a misnomer. Like I've been starting to call them like deep matrix networks, because I think neurons make me think of propagations, whereas matrix networks makes me think of matrix multiplications in a network. And so I think, again, that like we've sort of picked a name and we have these brain analogies, and then we teach people backprop. And I think all of this stuff is sort of does a disservice to what's actually happening when you're implementing these things. So historically, if you look at something like matrix multiplication, so matrix multiplication, as in really the forward pass, was invented in 1812. So it's an old algorithm, like by this guy to the right. And what's nice is that with automatic differentiation, the backward pass essentially becomes free to compute, as in you don't need to think about how you're getting the derivatives. You just know that you have a magical algorithm, you give it like a forward propagation, you give it a network, and it gives you the derivatives. And so I would argue, like a lot of ML papers today, you'll see in their derivations have like these long gradient derivations, and I liken these to sort of like long form division. It's sort of like it shows that you're smart and that you know how to do it, but for all intents and purposes, for most work, it doesn't really matter that you derive these things symbolically. And it's also why I think and I generally have this issue as well with the way we teach like math and physics, where we teach it like very formula, like it's very formula heavy. And I think instead, if you went first principles, it's like, okay, well, here's a simulator, for example, collect some data on the simulator, try to fit a few functions on it. You end up with something much more interesting and much more akin to how physics or math is actually done, as opposed to like this rote memorization of formulas and this idea of like fake rigor. So again, like, a lot of papers, they'll have some sort of incremental contribution, and then they'll talk about it for 8 pages and say like, oh, ImageNet is very important and deep learning is great and etc. And they'll sort of ramble on for 8 pages. When the vast majority of papers could be tweets, they could say, look, we changed X and Y and look at how nice our loss curves are. Unfortunately, you can't like publish tweets or cite them, but it's just like something to think about, where it feels that like for small contributions that do have an impact, like let's say the loss curves do actually look a lot better, like, well, why are you making the author go through the pain of writing out a paper? Like, why isn't the code itself really the citable piece of work? And I'm hoping like this will change over time. And I think I'm more optimistic about deep learning as opposed to other scientific fields to actually see this happen. So one thing you may have noticed, like when I talked about the power laws on how most work is not impactful, and it seems like a lot of us are sort of waiting to see like what OpenAI and DeepMind are going to do. And I want to like, help you explain that, like, why is this the case, right? So ML is fundamentally an empirical discipline. Like this means that for the most part, the ideas you have in your head sort of don't matter. Like what matters is the end level task performance. Like, is it actually better? Which means that like the people that are most likely to do the best papers can learn a lot by having lots of concurrent experiments. And well, like now think about it, it's like, well, let's say you know how to run lots of concurrent experiments and your peers do. Like now this is a feedback loop where you can all learn from each other and publish interesting stuff. And it helps explain why most of the cited and interesting work in machine learning today is coming out from industry labs more so than from academia. So we've also seen some weird incentives here where, you look at something like transformers, like when they first came out in 2017, it was definitely a very like interesting and breakthrough paper. But then we saw like all sorts of like incremental papers come out, like let's say, having transformers on proteins or on molecules or on images, or making them a bit fast or making them a bit smaller or making them go on longer sequence length. There's like a whole body of work that's just like forks of the original code base. And this sort of even reminds me of like the original DASPung, where, we want the transformer to go like harder, better, faster, stronger. And I think it's sort of like a lot of applied research at this point has reduced to this, just making transformers work better. And I think this is a real shame. To the point where I would even say that a BERT engineer is actually a full-time job now, like not ML engineer, a BERT engineer. And so the requirements for a BERT engineer is you need to know some bash. You need to really know how pip works because you're going to be pip installing all sorts of stuff. And you need to read English because you need to like read the readmes and figure out how the thing works. And then you just like wait for new HuggingFace models to be released. Maybe you'll see the new Yannick culture, like YouTube when it comes out, and that'll give you a good idea of the new transformer architectures. And then you can just repeat what Yannick said at your team meeting. And this is like actually a fairly reliable process right now where you can make a six-figure living doing this. And it also seems like you can't really opt out, right? Because let's say you downplay your achievements yourself. Like let's say you're the dog on the right and you're like, well, I don't really know a lot of ML. Like I'm just a pip engineer. You're actually going to make less money. Whereas a person who's like very confidently saying like, oh, I'm doing research, and maybe they're just like procrastinating all day and they're copy pasting stuff and they're just pip installing, are making over six figures. And so it becomes very difficult to opt out. Like the game theory of this makes it so almost everyone has to do this if they want like the high salary that comes attached with it. So I've actually formalized like this algorithm that I think like empirical labs are doing. So I call it graduate student descent. It's very similar to gradient descent, where instead of optimizing the gradients of an algorithm, you optimize over you optimize over the algorithm space. So the way this works is you initialize, so you don't know anything yet, and you find some sort of state-of-the-art paper on archive. Then you look for the code on GitHub and you make some random changes. And the first time one of your random changes works out, you publish it. And this is embarrassingly parallel over as many graduate students that you have, so you just keep doing this. And it also means, it also explains why architectures lately have been getting more complex. Like there's more pieces involved, like they're more difficult to understand, there's more ideas in them. Because if every time you take a new state of the art, it's likely itself to be complex and be generated by this process. And so now we end up with ever more complex architectures, as opposed to, again, going back from first principles and trying to understand like what works and what doesn't. Unfortunately, a lot of approaches that claim to have proposals to understand ML, like let's say things like saliency maps, to me, it reminds me a lot of astrology. It's sort of like trying to really peer into what something means without actually having any sort of deep understanding about it. It's sort of like a tangential understanding because like the pictures look pretty and you feel good about it. But actually, are you using them? Are you using these pictures to make the model better? And probably not. And in which case, they're probably not all as useful as you think they are. I also want to talk about scaling a bit because I have this impression that a lot of people in academia think that scaling a model is a question of just changing a bunch of arguments to a script. But I want to make the point that obviously scaling is very hard because you need to think about data parallelism, model parallelism, pipeline parallelism, like different locality mechanisms, MPI, you need like your data center communication protocols. So there's definitely a lot involved in making these things work. And I've seen, like, this is not my meme. Most of the other memes you've seen here are my own, but this meme specifically was very popular for a couple of years, where you have the statistical learner going like, gentlemen, our learner can't generalize the VC dimension, and something about unbiasing the kernel and using a soft margin. And then you have the clown stacking more layers. And I always found this meme very bizarre because it's sort of, you're the person advocating for more complicated stuff and getting worse results. I wonder who the clown is. And I think this is something to think about, where often, this sort of reminds me of the saying that I really love. It's how many angels can dance on the head of a pin? So the context behind that, like, this was a very deep question that a lot of philosophers debated in Constantinople around, like, how many angels can you actually fit on the head of the pin? And there were books, and people wrote their dissertations about this topic and wrote whole books. And in the meantime, the Ottomans just like invaded Constantinople, and then it just fell. So I think this navel gazing, it seems to work until it doesn't. So that's just like something to think about before you fall in love with your baby. So I often, another name I give this phenomena is fake rigor. So fake rigor is basically you add mathy sounding stuff to architectures to make it sound more compelling than it actually is. So for example, you say, I'm using a Fourier thing, or I'm using some symbolic math, and maybe you have like a long derivation that looks something like this, and it really intimidates people into thinking what you're doing is very important. But my general point on this has been, data sets are better than Twitter arguments. And what do I mean by that? Let's say you can't get state-of-the-art performance on something versus BERT, It doesn't mean that your proposal is useless, but it does mean that maybe you should think about a data set that you think will particularly showcase the strength of your algorithm. So literally overfit a data set to your algorithm. And I think that's a much more compelling way of convincing people that what you're doing is more interesting, as opposed to getting into Twitter arguments and how dare people don't appreciate your ideas or something like that. And I think this is best represented in Richard Sudan's Bitter Lesson. So the Bitter Lesson was a very influential blog post by an RL researcher called Richard Sudan. And in it, he noticed that basically the Bitter Lesson was that scale trumps complexity in deep learning. And so I showcased this meme, like, you can imagine that here you have like sort of the first year student doesn't know anything, and they're just saying, okay, Q learning is the best thing ever. I'm going to use it to make the agent go vroom vroom. And in the middle, you have like more of the typical researcher who's thinking like, oh, I need to do all this complicated math, and you can't just take a black box approach. You need to do this. But really, I think that the smartest people realize that, like, look, okay, scaling is really what makes these things work. And because most benchmarks are BS, and the reason they can be BS is because of the graduate student descent phenomena that we talked about. And so really, when you want to look at stuff that works, it's often the simple stuff, not the complicated stuff. So great. Now that I've sort of introduced all of these effects, like, what can we do about this, right? And really what I want to, like, the main thing, I think that we can do is basically opt out. And let me be more specific here. So again, so these are all the effects of publish repair. So I already covered all of these in the previous slide. And what I want you to think about it is this, like, essentially think of it as, well, it's a shame, like, let's say you're a junior person, you're starting your career, you should take advantage of this, like the fact that it's easy to make a lot of money for stuff that's not very difficult is great. It means that you can build a safety net for yourself. But as you get older, and once you build a safety net for yourself, what's really important is to start taking more risks to increase your upside. So start doing things like geometric deep learning. Maybe you want to do something with particle physics. But at least in the short term, sure, you can do a bit of BERT, but don't over optimize where that's the only thing you do, because then you're very likely to end up with an obsolete skill set in 2 years. And so when I think of this, like, a lot of people tell me, like, well, maybe this is because peer review is broken and we need to change the blind structure or whatever. I have some proposals there. And often these proposals will look like, a letter is sent to the NeurIPS committee saying, like, do you think peer review is broken? And then, the committee says, no, it seems just fine to me. Maybe you also email the NSF and you're like, hey, like, do you think the funding system is broken? Maybe it's over optimizing on deep learning as opposed to other more foundational areas. And they're going to say, nope, like, it looks good to me. And so, like, the point here is that you don't need approvals from central committees if you have a safety net. And if you have sort of a safety net can be both income and a reputation. And you can basically be a sovereign researcher. And what that means is that there's already people doing this, by the way, online. The fact that you can build your own tools, you write blog posts and get those cited, you can host your own conferences like people like Bill. You're financially independent, which means that you can afford to take risk. You don't mind learning anything. And you help crackpots flesh out their ideas as opposed to putting them down and letting them know that they don't know your terminology. So I think, like, another thing I want to talk about, and this is probably the biggest departure from the blog post, is what's not stagnating, right? And I have a few examples of areas that I think that are at the intersection of ML that I think are still extremely compelling and extremely active areas that are very, very fascinating to me. So one is software abstractions, right? So, I've been in deep learning for a while, like 10 years now. So I remember a day before we had like this layers abstraction and Keras. It kind of sucked, right? Because when you think of something like layers, like, this is actually when you read a paper, how you think about things. And so we created an abstraction that mimics the paper. And that's not necessarily not performant. And I often think this dichotomy between performance and abstraction is false. And the history of computing is sort of evidence of this, right? Like, computers have been getting more and more abstract without necessarily getting slower, because the range of problems that we tackle becomes more complicated and more involved. And I think the most interesting sort of path here has been what Fast.ai has been doing, where, as opposed to just thinking about the model building API, like stacking layers, they've thought of a whole bunch of stuff, like ranging from callbacks, where you can trigger behavior before a model finishes training or after training, so you can implement something like early stopping in one line of code. I also really like the pipeline API that's at the very bottom to the left. That lets you basically add a bunch of pre-processing steps in a pipeline and then do them one after the other. So these tricks matter. Like, and the fact that, historically, when we look at software patterns and we think the gang of four, we think like abstract factories, but machine learning sort of has its own abstract, like, software patterns. but I think are very important to better understand because it makes everyone more productive and lets us write more code in a much more enjoyable way and faster way. Another direction I'm very excited about is functional programming. So we've sort of already started to see this become mainstream with libraries like JAX and DEX, and now also with TorchFX, where you can start to think about a network as basically a function mapping inputs to outputs. And this becomes interesting when you combine this with some old literature in the hardware community on reversible computing, where the idea of reverse computing is like, let's say you have something like a 3D scene and you want to turn it into a 2D image. Like this is a rendering problem, this is graphics. But now let's say you could just, like you have a model that learned how to do this and you just reverse it. Like all of a sudden you have something that does photogrammetry, which is you take a 2D picture and now you can reconstruct the 3D scene. So this is useful if you're trying to build some 3D scenes of stuff in your bedroom or trying to make a movie or something. So it opens up like a whole other different range of problems, even though, and you basically get to solve some stuff for free. I also think one of the best blog posts I've ever read actually was this Chris Olah blog post on functional neural networks. And make note that this was not a published paper, it was just a blog post. And he sort of talks about like how you can build, for example, a bidirectional RNN using a single line of Haskell. And I find this stuff very compelling because instead of having, if models took 100 lines in the past, then to iterate on them, you need a lot of time. But if they take one line, then it becomes almost trivial to iterate because you change minor stuff and you end up with vastly different architectures. And you get closer to what the building blocks of this thing are. Another thing I'm very excited about is a neural ordinary differential equation. So I think the leaders in this space are the Julia programming language community. And so what they do here is that typically when we think of something like in neural networks, like often like we'll have Bayesian people think, oh, we need better priors, and I don't know, and often the priors are just Gaussians or something like that. But in physics, for example, like let's say you wanted to basically build a reinforcement learning model, right? But you want this model to also know but you give it as a prior the laws of physics. That means that the model doesn't need to learn the laws of physics from scratch when it's trying to do something. And as a result, the model converges a lot faster in a much more stable way. And this was just a question of, well, because the whole language is sort of differentiable end to end, if someone did write a scientific computing library, this makes it very easy. And they also have a software pattern, like a software abstraction called multiple dispatch, that makes functions work over multiple types very easily. And so it's sort of very deliberate software choices and a focus on science means that you can go solve like problems in reinforcement learning in a way that we didn't expect in the past, as opposed to maybe more recent work, which is just like, okay, well, we'll do a transformer on the episodes and that's probably going to work great. Like this is sort of incremental work, whereas this is foundationally different and I think much more likely to be fruitful in the long term. I also want to talk about HuggingFace. So HuggingFace is interesting because you'll see here at the bottom, this is their very first commit. They literally were like, okay, well, we're going to do a PyTorch version of the pre-trained BERT model. And then lo and behold, a couple of years later, they're talking about how they're going to break the monopoly of big tech and they're going to revolutionize everything. And it's going to be insane. And like, why? Like, how did a bunch of like random students and researchers how were they able to build a project that seemed to be as impactful as the projects that the largest companies were building? And I think it's because they built a community. Like basically they made their process scalable where people wanted to contribute and wanted to help them. And this is in direct contrast to something like OpenAI. So I think a lot of people, at least when I first heard about OpenAI, like they sort of lit a fire under me. I was like, wow, like OpenAI, like they're doing this epic stuff with games and stuff. But for some reason, OpenAI turned into a media and a service company. And because if you look at their blog posts, like they're highly polished, like their press releases are highly polished. They're very good. Their work is still very impactful, but they're really optimizing for people's attention. And so what that means is that they're effectively a media business. And so I had some academic friends that were like, aha, you see, it's a media business. But what I was thinking was like, well, actually, academia has also become a media business because it's sort of the work that generates the highest attention, that can get the most funding, can get the most press attention, can get the best students. So there's feedback loops that make this very inevitable. And I think this model works fine. It works well for academia, it works well for OpenAI, but HuggingFace is actually a platform. And what I mean by that is because, well, you can build like apps on top of HuggingFace. You can build different tokenizers. You can contribute different languages, different data sets very easily. Different implementations of BERT come in very quickly. People love it. Like people have an affection towards the library. They like using it. And I think this is sort of like one thing that's like very underrated about HuggingFace, and I think justifies like why they've been able to raise so much money and why their community has grown so strong over the years. I also think that, unfortunately, a lot of startups, like when you're thinking about like, well, if I'm an ML startup, like what should I do, right? You have the platform play, which is HuggingFace. You have the media play, which is OpenAI. And then you have the consultancy play, which is I will help you do ML, right? And I think this works fine for now because a lot of larger companies are having trouble retaining top ML talent because they want to go work at big labs because of the feedback loops I talked about earlier. So this makes the rise of the ML consultancies very natural. However, I don't think these are going to survive very long because if PIP is all you need, that means that if you have anyone who's a DevOps engineer, and there's many talented DevOps engineers in the world, like they can basically become very proficient machine learning engineers after spending a couple of weeks. Like this is the reality of the field, as much as we'd like to think otherwise, at least for the very applied side of things. I also think, another area I'm very excited about is when I look at something like reinforcement learning. A lot of the research tends to focus on Atari benchmarks, but I think what makes this space very interesting is that, well, any game can be a reinforcement learning simulator. So if you make a game in an engine like Unity, where you can define the goals for the unit, tell them like, well, they need to score, or maybe you'll give them an ability that they need to grow bigger. Maybe they'll figure out that, oh, if I'm bigger, I need to be a goalie, and if I'm fast, I need to be a striker. I find this hugely compelling. And so when you're trying to figure out, does a system learn to generalize with a certain kind of intelligence, you can make a game that tests exactly for that. And that's why I think games are sort of the ultimate data set and why I want more research to shift in this direction. Another thing that I'm very excited about that I didn't talk about in the blog post was biotech. So at a very high level, when you're thinking about something like DNA or a protein, so any you can think of it like sort of like this amorphous blob, like these liquids going around, like in space moving around. And so when you're trying to sequence this thing, like figure out like what is actually the alphabet and what does the sequence look like, well, you can use something like convolutional neural networks, or like let's say now you're trying to predict the 3D shape of the sequence. Well, you can use something like a transformer because tokens that have high attention between each other are likely to be folded on top of each other. So it's great. Now you can use transformers to figure out the 3D structure. And once you have the 3D structure, maybe you can use something like a graph neural network to do a classification or regression to say, well, does this cure this drug? Will this modification cure this person? And so I think this first principles thinking is very helpful. And for some reason, I don't know why when people think about ML, they just think about like language and images. But I think there's this whole army of problems that are absolutely fascinating at the intersections that are still low-hanging fruit. It's just that you need more domain knowledge, right? Because it's like everyone can read, but like fewer people can read proteins or understand how they work. So there's just more context there. Specifically with graph neural networks, like I find them very compelling because sort of all the interesting problems in the hard sciences are graphs. So when you think about like particles interacting, when you think about molecules, when you think about proteins or energy grids, like these are all networks. And the nice thing is that you can take a network, which is, let's say, a graph, you can represent it as an adjacency matrix. So now it's a 2D image. And then you can just feed it to sort of any deep learning like model, and you'll probably get like decent results. And obviously, there's like way better architectures that people have built to actually make this stuff work. But I think what this gets down to is that in CNNs, the breakthrough was discovering how to do translation invariance within the architecture. And so similarly, now it's become very popular in images to do like domain randomization, also in RL. Basically, you change the contrast of the images, you'll crop stuff, you'll change the contrast, you'll do all sorts of stuff. And what if we could build networks that could deal with these invariances? So basically light invariant networks, rotation invariant networks. And so this gets down to lots of interesting ideas that like, in group theory, and so using group equivariant networks and using like Lie theory. And we've already started to see these ideas used in algorithms like AlphaFold. Because what a protein does doesn't matter if you look at it, if you flip your head and look at a protein, it shouldn't change the function of it, right? It still has the same structure. So how do you build networks that can deal with this stuff very easily? I think it's going to be a very compelling research direction. Lastly, what I want to talk about is like the hardware lottery. So this is a great paper by Sarah Hooker at Google Research. And so what she talks about is that how a lot of algorithms end up winning out because they can run well on existing hardware. And not because they're actually better. And so I just one thing to think about is like, well, is deep learning a local optimum because of GPUs? So yeah, I mean, so with that, I think that's all I had. Really, if you take anything away from this talk, I want you to take away that core ML. So if you sort of the model.fit on images and languages, I think this space has stagnated, but the intersection certainly has not. Like you just need to basically I guess, have the courage and the safety net to pursue those problems. And I really hope, if after listening to me, that I'd encourage you to do this. And if you do have any interesting ideas, please feel free to share them with me. I'd love to hear them. And yeah, and I'm happy, more than happy to take questions. And thank you so much for taking the time to listen to me. I know it was very late for a lot of you.
Great. Thanks, Mark, for the very insightful the topics. Yeah, for folks, if you have questions, you can post to the Q&A. And if you prefer to speak to comments, any of the topics, feel free to raise your hand. I can promote you to the panelists for an open discussion. Okay, I see a couple in the Q&A. Mark, do you want to open your Q&A to go through them?
Okay. So how can graph neural networks be used for molecules, since different molecules have different graphs? So this is a question coming from Dave. Yeah, so I think like one way to do this is that you just pad all the graphs. And so you end up with a very sparse representation. So this is what libraries like Spectral do. And I think Biotech Geometric also does this for molecules. But I think to your point, where I find this really interesting is how do you make sparse graphs work? Because inherently, most graphs are very sparse. And I think this is more of a hardware question. So like, how do you make very sparse matmul work, where the sparsity pattern is dynamic? Because the way sparsity is typically dealt with, let's say in the latest NVIDIA releases, is that they take some sort of static fixed pattern, like I'm just going to skip these things, but you can't do that for something like molecule because you're going to skip important connections. So I think to your question is like, one, the trivial answer is you pad them. And then the more complex answer is we build hardware that does sparse matrix multiplication really well. So I also see Diarmuid, I apologize if that's not how I pronounce your name, but so it'd probably be useful to let people know how old a lot of the basics of AI ML are. This is why they stagnated. I think this is a good point, by the way. So I think really what they're referring to here is that like we have a short memory, right? Like a lot of times when we're reading papers, like we constantly feel this need to keep up because there's just like this army of papers being published like on a day-to-day basis on arXiv or Twitter. So there's constantly the psychological effect of FOMO that's very strong. And so that's why I've personally been trying more to read papers that are cited and at least 2 years old. And I generally found that they are surprisingly insightful and have discovered a lot of the core ideas, and that we're basically just reinventing the wheel in a less precise way. So I definitely encourage people to read what their elders had to say, because they figured out a lot of these problems. So Richard is asking, so nice talk, thank you. Could you tell a little bit more about ML agents? Are there good ones for testing algorithms for games? Yeah, so I actually have a couple of tutorials on this myself in my ebook. Also, the documentation for Unity ML agents I think is very good. But the main idea is that you basically make it, like if you know how to make a game, you basically make a game, and then you can say, this is what I want my world state to be, like what I want my agent to observe. You can even have a cone emanating out from the eyes. You say, this is what my reward function is, and then it spits out like a model for you that you can implement in your games. So it's actually very easy. Like you need to know two things. Like one, the basics of how to make a game, which is kind of hard, but Unity definitely makes it a lot easier. It's one of my favorite software tools. But also just how to hack rewards, as in for example, I got this issue where, I told my agents that just play, right? I want you to get as many goals as possible. And they figured out that the best way to get this result is not to play, because the score was always 0-0. So they didn't want to bother taking any risks. And so what I had to do was give them at every second, give them a small existential risk, like a small 0.1 risk. And that eventually encouraged them to start taking risks and go and score, where they would get like a much bigger payout. So yeah, Unity ML agents was great. I'd really recommend it. So Jeremy is also asking, so regraph, do you have a preferred implementation of graph tooling? Yeah, so I think that there's two libraries that I think are very good for this. I think Spectral, which is a Keras-based library for graph-based deep learning, is very, very good. It's very clear. And also PyTorch Geometric, I think, is very good. It has basically all of the core algorithms. And so then when you're thinking about a specific algorithm that's interesting, you can just look at something like graph convolutional networks. It's sort of like the most basic architecture, which will relate back to something we'll talk about, because I see one question is on quantum, and I'll get to that in a second. And that was by Thomas Kipf and Welling, and Welling does a lot of stuff in quantum. So maybe I'll answer that question next. So R. Burns is asking, how does quantum computing shake up the ML field? So I think there's sort of two parts to this question, and I will caution you that I'm not a quantum computing expert, but this is where I see the field becoming interesting. So on one hand, I think that there's a lot of ideas in quantum physics that are interesting, like the ideas of different invariances and how you come up with all the fundamental particles that work and stuff. A lot of them is based on like Noether's lemma and whatnot. And so I think having more modules in deep architectures that deal with invariances, whether it's rotations or rotations under specific kinds of rotations or translations or whatever, or lighting or whatever, I think this is going to be very compelling. But I also think when you're thinking about, well, like there's the quantum simulator aspect, which is, well, maybe, you want to do something like like let's say you own the Large Hadron Collider and particles are colliding into each other. The particles are going to collide, and then it's going to create this like complicated graph with like all the ionized like atoms in this space. And so I think being able to take a graph like that and analyzing it, I think is also going to be very compelling. And now I think maybe what you also may be referring to is like, well, what can we do with something like quantum? Like, let's say we had quantum computers, can we do ML faster? Like, I don't know. Like, I think I've read some papers a bunch over the years about this, but I never really understood them. So Al Mercado is asking, like, what about enterprise platforms like Cloudera, or where K8s is used for Spark clusters? Like, where is that going? I mean, I think like Cloudera is a great company, right? So as long as they have customers that are interested in using the expertise and tools, they'll continue doing well to the future. I also think that this direction towards more in-memory compute, I think, is great, because you can always like scale up as opposed to scaling horizontally, just like get more RAM, and then everything's going to run blazingly fast. And so, yeah, I mean, like I definitely see these ideas like benefiting, and I think where I find the cross section interesting there is that when you think about in ML, like fundamentally, well, how do you really do efficient data and model parallel? Like how do you deal with this, and how do you deal with communications? In this case, I think there's a lot of innovation that a lot of compute providers are providing there that can make this stuff a lot better. So now Andrea is asking, so do you see some promising directions in systems that generate world model and some sort of long-term memory? Yes, actually, I do. So two parts here. So the first one, for example, is like, let's say in graph neural networks, there's this really interesting architecture called temporal graphs, which basically replaces each node with an RNN, and then the RNN can remember its past interactions with other nodes. So I think this is always going to be compelling. But I also think that I'm very optimistic about what Julia is doing for world models, as opposed to just basically learning a world model. Well, we already know the laws of physics, right? So they're already a pretty good prior. And so how do we incorporate that more into these systems, I think will be very compelling. So R. Burns, is AGI a false goal? I think it's a good question. I do think it is somewhat of a false goal, because I think back to the HuggingFace and OpenAI analogy, it's sort of yes, AGI will unlock infinite capability if it gets figured out, but the likelihood of that happening are very slim. And you can build a multi-billion-dollar company on something a lot less speculative than AGI, as HuggingFace will most likely do. So Eric Wong is asking, so any recommended tools or libs for distributed GNN training for large graphs? This is a very good question, actually, Eric. Thank you. So I think the people I've seen do the best work there are the DGL team at Amazon, and then also Python Geometric has some graph clustering libraries. But what's interesting about distributed GNN training is that it's a hard problem. So what people will do is either they'll subsample a graph, so like they'll cluster it and put it on multiple machines. That way it fits on the device memory of an accelerator. Or what they'll do is they'll just like compress it. They'll just compress it down. I think there's also some recent work by, again, Michael Brownstein's team to not do graph clustering. But what I also found hilarious about this space is that there's no good answer, because a lot of the leaderboards for graph neural networks actually use CPUs, because yeah, they're slower, but then you can just plug in as much RAM as you want, as long as you can afford it. So Thomas is asking, so awesome talk, a bit off topic, but anyway, Mark, I would be interested in your thoughts about the alignment of ML, especially regarding ethic, moral questions connected to our society. Maybe it's even helpful to have a temporary stagnation to catch up with public discussions, procedures, and policies. Yeah, I mean, like, I will caution here by saying, I don't know enough if these temporary moratoriums would help. Like, I think I would need to maybe research more, let's say, other impactful techniques, like, let's say, nuclear or stuff like gene editing, like CRISPR, like those benefit from more moratoriums and more discussion. And I think I would just follow legal precedent there. But it's like, I'm embarrassed to say, like, this is not a space I know a lot about. So Darren is asking, so great talk, Mark. Any tips on getting started in an open source ML project? Hard to do this outside of a full-time job. I mean, yeah, it is definitely harder to do in a full-time job, which is why something like a master's, if it's a good program, always helps. Like, that's what I did to get my first ML job. But I will say that often you'll realize that with open source, there's so few people doing it, that just by you reaching out and making a minimal contribution, whether it's an example or clarifying some issues or refactoring some stuff, it can be a lot easier. So I will say, I mean, it just all depends on your time and maybe like also your seniority in your career. Like maybe if you have a lot of money and you have a good reputation, you can afford to just take more time off, maybe even leave your job. But if not, if you're still junior and you need the money, by all means, just do that. Because I think industrial ML, I think at this point is more interesting than academic ML. So Nitin is asking, so quantum ML, is it revolutionary in terms of finding global minima or solving large-scale problems? I will say it's probably too early to answer that. Like, I don't know. I think the devil's in the detail there. So Nitin's also saying, well, to elaborate more on my quantum ML question, if yes to previous question, do you think investment in quantum ML is an overkill or for an organization to large scale and high number of inputs-based optimization problems? No, I mean, like I think it's very important for any company to do fundamental research, right? It's just a question of ratios. Like, I don't think the community is depending on innovations in quantum ML to really move forward. But if someone does build something very compelling there, like, I'll be the first to use it. I'm not an expert to fully answer that. So I also see a bunch of questions in the chat. Oh no, that's here. Okay. Yeah, I think those are all the questions I see so far.
All right. Yeah, I think the question already answered in the Q&A. Great. So we still have a few more minutes. Anybody have more questions? Feel free to post in the Q&A. Again, anybody want to speak, to ask questions or comments or share your thoughts? Feel free to raise your hand. I can promote you to panelist to speak.
All right, thank you so much, everyone. I really appreciate the kind words. And thank you for taking the time to listen to me. I know it was late for a lot of you.
Hey, Andrew, you are on stage.
Yeah, thanks. Thanks, Mark. It's a nice talk. I actually realized that I've read your article when it came out, but I didn't make a connection between this talk and that article before you started. And
that's a good surprise.
yeah, so I have actually more comment and like maybe a little bit of call for collaboration. So there is a really interesting AI benchmark called Abstraction and Reasoning Challenge by Francois Chalet, that's the main author of Keras. It's basically a test for generality of like intellectual intelligence system, and like it's mostly a benchmark we can call for program synthesis, and it's really hard to do it with our usual differential methods because there's just you can't really differentiate over the discrete code, and so yeah, I see this as a really interesting direction of what do we do with non-differentiable systems. It's one hand, and basically, yeah, I'm working for already several months trying to do it. It's a really interesting project with a lot of uh, optimization challenges. And if somebody wants to uh, talk to me, look into it further, I would be really happy.
Yeah, I mean, like, feel free to reach out with like more details if you want. Like, just send me a DM on Twitter or something. I'll be happy to take a look. But I agree with you in that like better data sets I think are very compelling because, like it's. I'm pretty sure we've overfit, for example, on ImageNet at this point. Like, it's sort of, like there's lots of interesting problems, and I think being too obsessed with benchmarks is very counterproductive, because it doesn't mean that it's going to work well for a real system. Whereas, like, I think the work that you mentioned that Cholet was doing, I think definitely re-challenges our perceptions. I think the past works I've seen on stuff like program synthesis and code autocomplete using deep learning, I think a lot of them have flopped, and others have tried to simplify the problem by picking, let's say, code from a template as opposed to just writing code. So I think that's maybe one way to simplify the problem, but I think the hard version of the problem is more interesting. So yeah, I mean, happy to talk more about it. And I'd encourage anyone listening in to reach out to Andre as well.
Okay, thanks.
We have one more question in the Q&A coming up.
Yeah, so I see Douglas asking, so is there a thing that people think quantum means larger, faster, and not some domain related to quantum mechanics? Yeah, actually, that's an interesting point, Douglas. I think it's more of a comment as opposed to a question, but yes, I think you're referring to, some people are saying, well, can we have quantum ideas, as in invariant ideas in deep learning? And some people are saying, well, maybe we can use deep learning to accelerate quantum simulators, and other people are saying, well, with quantum machines, we can accelerate with deep learning. I think these are all get bundled up under quantum ML, but I think they're very different and probably very different kinds of people tackling each of those problems.